Hello everyone, I'm Seunghoon from Korea University. Now I present our paper called V0Finder, which was co-worked with Dongwook, Sunghan Park, Heejo, and Sven, Dietrich. The goal of this paper is discovering the correct origin of publicly reported software vulnerabilities. Specifically, we coined the term vulnerability zero, which means the software and its version where a vulnerability originated. The reason we attempt to discover the VZ is that the incorrect VZ can cause several problems. For example, the incorrect VZ lead other developers to unintentionally overlook the propagate vulnerability and to delay patch deployment. As a motivating example, we introduced the CVE 2017-0700 case. Its description states that it is a remote code execution vulnerability in the Android system. However, we confirm that the correct VZ of this CVE is JPEG compressor reused in RipGDX, which is further reused in Android. In this situation, developers reusing vulnerable version of Android can easily resolve the vulnerability because the CVE has been reported as an Android vulnerability. However, developers reusing only the vulnerable JPEG compressor fail to detect and patch the vulnerability in a timely manner because they do not interest in the vulnerabilities of Android. We succeed in reproducing the vulnerability in the latest versions of 3 popular software projects. Note that all reported vulnerabilities have been patched as a response of our reports. To prevent such problem, our goal is to discover the correct VZ of a vulnerability in an automated way. For example, in this case, we will discover JPEG compressor as the VZ of this CVE, not RipGDX or Android. There are 2 major challenges to discover the correct VZ. First, because the timestamp-based metadata of software can easily be changed, the VZ may not be the vulnerable software with the earliest birth date. Therefore, we cannot solely rely on the timestamp-based metadata. Second, the syntax of a vulnerable code frequently changes while the code is reused in other software. So we should address the syntax priority of vulnerable code. To overcome the challenge, we present V0Finder, which is the first approach to discover the correct VZ of a vulnerability. We use a graph-based approach instead of using timestamp-based metadata. That is, V0Finder generates a vulnerability propagation graph for each vulnerability, where its nodes represent the vulnerable software and its edges indicate the propagation directions. In other words, we convert the problem of discovering VZ into a problem of finding the root of the vulnerability propagation graph. This is an example graph for CVE 2017-0700. Using this graph, we can easily discover the VZ JPEG compressor and also trace software to which the vulnerability has propagated. To generate a graph, V0Finder first detects all vulnerable software that contains a specific vulnerability and then identifies the propagation direction between every vulnerable software pair. First, V0Finder detects vulnerable software programs containing a vulnerability. Considering syntax priority, we use the method of detecting similar vulnerable clones. Here, V0Finder uses the vulnerable function and patch information of a vulnerability. V0Finder first extracts all functions from a software program and then applies the locality-sensitive hashing to all the extracted functions, which can measure the similarity score between 2 different hash values. After that, V0Finder measures the similarity score between the hash of vulnerable function and the hash of functions in software. If a function is similar to the vulnerable function, and if it contains all the deleted patch lines while does not contain any inserted patch lines, V0Finder determines that the function is a vulnerable clone. If a vulnerable clone is detected, the software program is considered as vulnerable. All the detected vulnerable software become the nodes of the graph. Next, V0Finder identifies the propagation direction between every vulnerable software pair. Instead of using timestamp-based metadata, we focus on a reuse relation between the two vulnerable software. If software S1 reuses software S2, and if the two software share the same vulnerability, we can determine that the vulnerable code has propagated from S2 to S1. To identify reuse relation, V0Finder utilizes three key factors: source code, path information, and metadata files. Specifically, if S1 contains the entire codebase of S2, or if the path of any common source file in S1 contains the path of the file in S2, or if S1 contains a metadata file located in the root path of S2, then V0Finder determines that S1 reuses S2, which implies that the vulnerability propagates from S2 to S1. According to the identified propagation directions, V0Finder connects the corresponding vulnerable software detected in phase 1. As a result, the vulnerability propagation graph is generated. Finally, V0Finder discovers the VZ by finding the root of the generated graph, which is the starting point of the vulnerability propagation. More details and justifications of our techniques are explained in the paper. To evaluate V0Finder, we collected more than 5,000 CVEs from MVD and itch trackers, and also collected more than 10,000 popular open source software from GitHub. We applied V0Finder to discover bridges for the collected CVEs, and then compared the discovery result using the CPE provided by the MVD, which contains the vulnerable software name and its version information of a vulnerability. As a result, we confirmed that V0Finder successfully discovered the correct bridges for 95% of collected CVEs. Surprisingly, V0Finder found that 96 CVEs for which current vulnerability databases provide the incorrect VZ. The impact of the correctness of VZ will be introduced in the later slide. Although V0Finder could discover the correct bridges for most cases, it reported several false alarms. Specifically, when VZ does not exist in our dataset, or when V0Finder failed to identify some reuse relations, the generic graph may have multiple roots or does not have any root. Yet, we confirm that V0Finder can discover the correct bridges with a high precision and recall more than 95%. We then analyzed the impact of bridge discovery. In this part, we define the success and the elapsed time for vulnerability detection. In phase 1, V0Finder detected vulnerable software programs containing a vulnerability. If the latest version of vulnerable software does not contain the vulnerability, we consider that the software succeeded in detecting and patching the vulnerability. We further call the time required to detect and patch the vulnerability as the elapsed time. We first analyze the correlation between the success rate of vulnerabilities and the correctness of VZ. In the cases of CVEs with the correct VZ, more than 85% of vulnerable software succeeded in patching the vulnerability. In contrast, surprisingly, we confirmed that only 36% of vulnerable software could patch the vulnerability in the cases of CVEs with the incorrect bridges. Next, we investigated the elapsed time for patching a propagate vulnerability. Even when the vulnerability was successfully patched in the affected vulnerable software, we found that CVEs with the incorrect VZ require additional 200 days to patch the vulnerability than that with the CVEs with the correct VZs. From our experiments, we found that some CVEs are reported with the incorrect VZ. In that case, the incorrect VZ hinders detection and patching of propagate vulnerabilities. Therefore, to enable developers to detect and patch propagate vulnerabilities in a timely manner, we suggest that the task of discovering the VG should be accurately performed with a system such as V0Finder. This is our conclusion. We found the correctness of VG has a significant impact on the appropriate detecting and patching the propagate vulnerabilities. In response, we presented V0Finder for the first time to discover the correct VGs of software vulnerabilities. Equipped with VG discovery result from V0Finder, developers can address propagate vulnerabilities in a timely manner. This is the end of my presentation. Thank you for your attention.